You've probably used one today, maybe even in the last hour, and didn't think twice about it. But what if I told you that you had to build one? We're talking about a service that looks so simple on the surface, but underneath, well, it's a monster of an engineering challenge. Today, we're going to deconstruct the URL shortener. You know the drill, right? You've got this ridiculously long, messy URL. You pop it into a service like bit.ly, and boom, out comes this perfect, tiny link that's easy to share. From the user's side, it's over in seconds. It's clean, it's simple, and it's just incredibly handy. Okay, but let's flip the script. What happens when it's not just you using it, but millions of people? All of a sudden, that simple little service needs to handle an absolute fire hose of traffic. We're talking 10 billion clicks, redirects, and requests every single month. Now that is where the real engineering starts, and that's exactly what we're going to design right now. So get ready, it's time to dive headfirst into the blueprint for a system that doesn't just survive at that kind of scale, but actually thrives in it. First things first, before we can build anything, we have to understand the scale of the problem. These numbers are going to dictate every single decision we make down the line. So let's do some quick back-of-the-envelope math to see what we're really up against. Let's start with the writes. Now, a write operation is just any time someone creates a new short link. We're going to estimate that our system needs to handle about 100 million of these every month. That breaks down to about 40 new links being created every single second. That's a lot, for sure, but it feels manageable. But now, let's talk about the reads. A read is a redirect. It's someone actually clicking on one of our short links. And this, my friends, is where the scale just completely explodes. We're talking 10 times billion reads a month. That's about 4,000 requests hitting our servers every second of every day. And this chart, well, it says everything, doesn't it? The reads just completely dwarf the writes. We're looking at a 100-to-1 read-to-write ratio. What this tells us is that for every one time a new link is created, 100 links are getting clicked. Our system isn't balanced at all. And that brings us to the single most important insight for this entire design. This one fact is the key that unlocks the whole puzzle. Our system is massively, overwhelmingly read-dominated. Everything we do from this point forward has to be optimized for one thing: lightning-fast, high-volume reads. So, how do you tackle a read-dominated system? Well, you don't build one service. You actually build two. We're going to literally split the work into two separate paths, and we're going to tune each one for its specific job. Just look at the goals for each path. On one hand, you've got the write path. Its job is creating links. It needs to guarantee that every single link is unique and that the data is stored correctly. Consistency is king here. On the other hand, you have the read path. Its priorities are totally different. It's all about extreme speed and high availability. If the links don't redirect, the whole service is down. And this split gives us our four core components. We'll have an app service that handles the slower, more careful work of writing new links. Then, a totally separate, lean and mean redirector service that does nothing but handle reads at blinding speed. Of course, we need a scalable database to be our source of truth. And finally, the real secret sauce: a super fast in-memory cache that acts as our speed layer. Okay, let's get our hands dirty and build this thing, starting with the write path. How do we actually take that long URL and forge a brand new, unique short link for it? It's a really clean three-step process. First, we need a number, a big number that's guaranteed to be unique. Second, we have to turn that number into the short text that you actually see in the URL. And third, we just have to save the connection between our new short code and the original long URL. Let's break each of those down. So, how do you generate a unique ID 40 times a second without all your servers stepping on each other's toes? Well, you use a battle-tested solution like Twitter's Snowflake algorithm. It creates a unique 64-bit number that's also sortable by time, and, this is the best part, it doesn't need a central server to coordinate things. This is an absolutely perfect fit for a language like Go, whose whole concurrency model with Go routines makes it incredibly efficient to spin up thousands of these ID generators without breaking a sweat. So now we have this giant 64-bit number, but we need a short, friendly string for our URL. That's where base62 encoding comes into play. Think about it like a different way of counting. We're used to base 10, right? The digits 0 through 9. Well, base62 uses 62 different characters,
all the lowercase letters, all the uppercase letters, and the number 0 through 9. This lets us pack a huge number into a very, very small space.
And the result is pretty dramatic. A giant number like 100 billion, which is way too long for a URL, gets squished down into this neat 6-character code, P9ME3A. That's the magic of base 62 right there.
And finally, we just have to store that mapping. A NoSQL key-value database is the perfect tool for this job. You can think of it like a giant dictionary. We only ever need to do one thing, look up a value, which is the long URL, bytes key, which is our shortcode. So by making that short underscore code the primary key, we're telling the database exactly where to look. It's not a search, it's a direct, blazing fast lookup.
All right, we've forged the link. Now it's time for the most critical piece of this entire system, the read path. This is where we have to handle those 4,000 requests per second. And this path has one mission and one mission only: be as fast as humanly or computerly possible. The logic here is just beautiful in its simplicity. A request for a short link comes in. The very, very first thing we do is check a super fast in-memory cache, something like Redis. If the link is there, bam, we redirect immediately. If it's not there, what we call a cache miss, only then do we bother going to the slower database. And once we get the answer, you better believe we put it in the cache so the next request is fast. This whole strategy has a name. It's called the cache aside pattern, and it's a fundamental tool for any engineer building scalable systems. Basically, your application code itself is responsible for managing the cache. This gives you total control. And, most importantly, it acts as a shield, protecting your database from getting hammered by thousands of requests every second. And the performance difference here is just staggering. A cache hit, which for any popular link should happen over 99% of the time, gets a response in under 10 milliseconds. That's basically instant. But a cache miss? That forces a trip to the database, pushing the response time to 100 milliseconds or more. That's 10 times slower. So the cache isn't just a nice-to-have feature, it's the absolute heart of our system's performance. So we've designed the whole system. But let's zoom out. What are the big picture principles we can take away from this and apply to other problems? Let's recap the core lessons we've learned here. Here are the key lessons you can really apply to almost any system you build. Number 1, always look to separate your read and write paths. 2, figure out your single most frequent operation and optimize it relentlessly. 3, treat your cache like a first-class citizen. It's not an afterthought. 4, choose the right database for your specific access pattern. And 5, solve your unique ID generation problem early so it never becomes a bottleneck down the road. And there you have it. That's the blueprint for a URL shortener that can handle billions of requests. So I'll leave you with a question. Now that you have this mental model, this idea of splitting systems into read and write paths, what other services do you use every day? Think about your social media feed or an e-commerce site. How might they be broken down in the exact same way? Because I promise you, this pattern is everywhere once you start looking for it.